Hey guys, Kenna here. So today we're going to be looking at thermodynamics and entropy. So thermodynamics, as you can go ahead and guess from the name, is about changes in temperature. And so we're going to start looking at the laws of thermodynamics and how this relates to the kinetic molecular theory. Okay, so let's jump right in and take a look at our essential questions for today. Number one, what is thermodynamics? You may be able to figure most of that out just from the name. Number two, what are the laws of thermodynamics and what do they mean? That'll be a big focus of what we're going to look at today. Number three, can you explain a thermodynamic system in terms of the system and surroundings with respect to the laws of conservation of energy? And number four, what is entropy, a measure of, and how does that relate to life? All right, so thermodynamics is a branch of physics concerned with heat and temperature and their relationship to energy and work. Okay, now remember energy and work are in the form of joules. That's the primary unit we use. And heat and temperature are typically a measure of thermal energy. So it's still going to be measured in this form of joules. In particular, it describes how thermal energy is converted to and from other forms of energy and how that affects matter. And we can tangentially kind of relate this to Einstein's E equals mc squared, which relates energy to matter. Okay. So thermal energy is the energy a substance or system has due to its temperature. This is the random kinetic movement of the molecules within the material. Okay, so thermodynamics involved measuring this energy, which can be really complicated. And so we're not going to do intensive studies of this in terms of how you would calculate the exact amount of thermal energy, although we will relate it to what we talked about in terms of specific heat. Now, when we start looking at the system studied in thermodynamics, they can be a large number of atoms or molecules interacting in very complicated ways. But if these systems meet the right criteria, which we will call equilibrium, they can be described with a very small number of measurements or numbers. This is often idealized as the mass of the system, the pressure of the system, and the volume of the system, or some other equivalent set of numbers. And so let's go ahead and highlight that again. These should sound familiar because we talked about something similar to this when we were going over the gas laws, the combined gas law. Okay. So if we go ahead and take a look at this, we're going to go ahead and describe them in terms of their mass, in terms of their pressure, and in terms of the volume. Okay. So those are the three key pieces that we typically go ahead and look at when we're going to go ahead and look at thermodynamic system. So let's take a look at the laws of thermodynamics. Now, there are three principal laws that we're going to talk about today, and each one leads to the definition of thermodynamic properties, which will help us better understand and predict the operation of a physical system. The first law of thermodynamics says that energy can be changed from one form to another, but it cannot be created or destroyed. This should sound somewhat familiar in terms of the law of conservation of energy or the law of conservation of momentum. But ultimately, the total amount of energy and matter in the universe remains constant. We're going to simply change it from one form into another form. All right, so that was the first law. Now we've got the second law of thermodynamics. The second law of thermodynamics measures the disorder in an isolated system. So, if a system is not in equilibrium, the disorder in that system will tend to increase over time, approaching a maximum value when it reaches equilibrium. So, we got to think back to like what we were talking about in terms of diffusion back in your biology days. If you have a concentrated amount of a substance, it's going to eventually spread out to the point where it's evenly distributed everywhere. This is equilibrium. Okay. Which leads us to the third law of thermodynamics. As temperature approaches absolute zero, remember absolute zero is where there's no net internal um, random movement in terms of the kinetic molecular theory, then the entropy of a system approaches a constant minimum. Okay, so the disorder or disorganization, because everything is going to become more uniform. Now, in order to truly appreciate this, all of these laws actually, we need to better understand the term system and surroundings. So, when scientists discuss a thermodynamic value in reference to a system, it is everything that is enclosed within a particular unit. Okay. Anything that's not closed in that unit is what we would consider to be the surroundings. So the systems and surroundings are somehow going to be separated by a boundary, and that has to be determined if we're going to go ahead and mathematically represent this particular system and its energy. Okay. Now, this is important to keep in mind because this relates directly back to what we talked about in terms of frame of reference. What qualifies as part of the system? What qualifies as part of the surroundings? So you have to identify these before you do any problem solving related to these things, just like when we were setting the frame of reference for direction of motion with respect to things like momentum. Okay? So if a system is a gas in a container, then the boundary is simply the inner wall of the container itself. Everything outside of that boundary then is considered the surroundings, which would include the container itself. So that would be an example of a thermodynamic system. So the boundary must be clearly defined. And this is, again, I keep coming back to this concept, but we really need to understand that this is a measure of frame of reference. Okay? Because we can go ahead and establish any frame of reference, and that's going to change what our system and surroundings are. But in terms of energy coming in, okay, and energy going out, we have to realize that those boundaries that separate the system and the surrounding have to be recognized, identified, and kept closed for the most part. So if matter is not able to pass across the boundary, then the system is said to be closed. However, if matter can be transferred across that boundary, then the system is considered to be open. A closed system may still exchange energy with surroundings unless the system is an isolated one, in which case neither matter nor boundary can then pass across the boundary. Okay, so again, that's the idea of an isolated system. So an isolated system, no matter, no energy pass across that boundary. All right, so what does this mean in terms of the first, second, and third laws of thermodynamics? Let's take a closer look. With the first law of thermodynamics, this is known as the law of conservation of energy. We've mentioned it before, but this is just a restatement of the law of conservation of energy. Okay, oops, too far. So, law of conservation of energy. And we have gone over this before, so we want to make sure we keep that really clear in our heads. And this states that energy can be neither created nor destroyed. Energy can only be transferred or changed from one form to another. For example, turning on a light would seem to produce energy. However, it is converting electrical energy into the light energy that you are seeing. Okay. All right. Now, when we think about this in terms of energy, we can express this relationship in terms of the amount of work done on a system. So we'll tie this into our work and power equations from last term. Okay, any change in the internal energy, which we'll go ahead and call delta U here, of a system is given by the sum of the heat that flows across the boundaries and the work that is done on the system by the surroundings. Okay, so Q represents the heat added to the system, and W represents the work done by the system. So when work is done, energy is being removed and therefore is not available to create a change in internal energy. So this law says that there are two kinds of processes, heat and work, and that either can go ahead and lead to a change in the internal energy of a system. Since both heat and work can be measured and quantified, this is the same as saying that any change in the energy of a system must result in a corresponding change in the energy of the surroundings outside the system. So if we were to go ahead and set up a boundary, okay, let's go ahead and say we set up a boundary. I'm going to label this as the system, and outside here is the surroundings. Now, what this means is that if the energy in the system goes up, then that means that the energy in the surroundings must go down. And likewise, if we go ahead and see the energy in the system go down, then the energy in the surroundings must go up. This type of relationship is direct between the two parts of the related units. Okay, so the system and surroundings are connected to each other. And because of the first law of thermodynamics, energy can neither be lost or created, and therefore simply must be moving from the system to the surroundings to the system, or changing form within one of those two purviews. Okay. So let's go ahead and take a look at the second law of thermodynamics. The second law of thermodynamics says that the entropy of an isolated system will always increase. The natural tendency for a system that is separated from its surroundings is to get closer and closer and closer to equilibrium. Now, that creates a small amount of problem for us as human beings. We are, in many respects, an isolated system. We have to keep our body functioning and keep it growing and keep it doing its normal everyday things. Otherwise, its natural tendency is to decay and to break down to where there's an even spread out of all of our molecules. Okay. So this is with respect to thermal equilibrium, but we're looking at this maximum amount of balance or equilibrium. So the simplest way to put this is that the entropy of the universe only increases and never decreases over time. So if we go ahead and take a look at this, and this is related to a lot of our cosmology. So if you've ever studied any cosmology and astronomy, we start realizing that this is expressed in terms of what they call the big chill. Okay, let's call that the big chill. And that ultimately what this says is that over the long haul is that the entropy increases over time until the universe goes ahead and reaches equilibrium. But at this point where the universe reaches equilibrium, all of the thermal energy is spread out evenly everywhere, so there are no pockets of heat and pockets of cold, but simply a uniform temperature everywhere. Okay, and that temperature of space is pretty cold. And so this is again what's known as the big chill. This is based on the laws of thermodynamics. And in particular, okay, dynamics, and in particular, the second law of thermodynamics. All right. Okay, so when we start looking at this, we are interesting because we as humans are an example of the opposite of entropy. We are not moving towards dispersal into an equal state everywhere in the universe. And so every time a baby is born, you are looking at an example of anti-entropy. And this is the concept that was put forth by physicist Erwin Schrödinger in 1944. He defined living matter as that which avoids the decay into equilibrium. This definition is really looking at the second law of thermodynamics, which says that entropy always increases. Entropy then is often referred to as chaos as disorder, but in reality, it's simply the spreading out of energy towards a state of uniformity. And so Schrödinger says living things are able to postpone this trend. So, how do we do it? Well, it turns out you do it by eating, by sleeping, all those things we talk about that help you to go ahead and grow and develop. Okay? Because your matter is matter from the universe. And you are bringing that matter together in some organized way to go ahead and create you. And so when we start looking at entropy, okay, heat is really a measure of disorder. And in physics, disorder is referred to or quantified as entropy. And therefore, entropy is a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work. And so in biology, we talk a lot about the fact that we have these chemical processes like metabolism that lose energy to metabolic heat. Okay. Remember, according to the second law of thermodynamics, you don't ever actually lose heat. Actually, it's the first law of thermodynamics. But according to that first law of thermodynamics, you don't ever actually lose energy. It's simply converted into a different form or converted into matter according to Einstein's equals mc squares. So what we say is when we lose energy to metabolic heat is that it's simply being converted into a form that we can't really recapture. And so we're moving from this pocket of isolated heat, and it's going to be moving in all these different directions, spreading out towards uniformity. Okay, so that's really what we mean. Is it's not that it's lost. Okay, so it's not lost, but it's unavailable to do work. Okay, so that's really what we're looking at. And so, just as the constant increase of entropy is the basic law of the universe, so is the basic law of life to become more highly structured and to struggle against entropy. All right, so that's really what we're looking at in terms of this anti entropy. So, just as the constant increase of entropy is the basic law of the universe, so it is the basic law of life to be very more highly structured and to struggle against entropy. This is from Vaclav Havel in 77. So, in many respects, the process of your body building itself up and maintaining itself is anti entropic. And that's only possible because of the work our bodies do in converting our food and using the time to rest to rebuild, replace, and repair. So, this is why it's so good to have good nutrition. This is why it's so good to make sure you get enough sleep at night. Okay. Okay. And that leaves us with the third law of thermodynamics. The third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. And once again, this relates to what we talked about before in terms of the big chill, if you know anything about cosmology. So once again, this is what we call, excuse me, this is what we call the big chill. Okay, so big chill, where if you think about the universe as the ultimate system and you spread out all the energy so that it's uniform everywhere, the amount in any one specific place is so low that the temperature is incredibly cold and essentially most of the motion in the universe stops and it becomes really cold. Okay, so this is one of three potential ends to the universe. If we talk about the alpha and the omega, this is what we're talking about as one of the potential options. Okay, the other two are the big crunch and the big rip. And if you want more information on those or you want to talk about those, please feel free to let me know and we can go ahead and go over that. All right. All right, so the last thing I'm going to introduce, but I'm not really going to spend any time on, is what's known as enthalpy. Now, if you go ahead and take chemistry, you'll get more time going over enthalpy, but essentially it's defined as the sum of internal energy E plus the product of the pressure, P, and the volume V. And the symbol H is used to represent enthalpy. So H equals E plus P times V. And so this is related to the gas laws as well. And so you can see that in terms of the pressure and the volume here. Enthalpy can then be related back to specific heat, as both enthalpy and energy are measured in joules. So once again, that joule unit is really important here. We won't focus on enthalpy here, but if you take IB Chem, you'll definitely cover this more in detail. All right, guys, that's what I've got you for today. I hope you guys are doing well. Stay healthy, stay safe, and we'll talk to you soon. Take care. Bye-bye.